Good afternoon, friends. As we discussed in the previous class regarding the Navier-Stokes equation, there is no derivation for this equation as per the syllabus, but there is only the illustration of the final equation. The very important next topic of this fluid dynamics is a flow of viscous fluid between two parallel plates. Figure shows two parallel plates. Both are stationary plates, fixed plates, and in between we are going to observe there is a fluid passing through these parallel plates, and ABCD is the fluid element we have considered for the analysis of viscous forces of fluid between two parallel plates. Now, as I told you, so we have considered an element ABCD, and P into delta Y into 1 is the pressure force here on the left hand side on the face AB, and P plus dP by dx into delta Y into 1 will be the pressure force on the face DC. There are two shear stress acting on the two faces AD and BC, and the corresponding shear forces are given in this figure. Now, here in this figure, the ABCD, what we have considered the fluid element. So on this fluid element, the following forces are acting. One is P into delta Y into 1 on the face AB, P plus dou P by dou X into delta Y into 1 on the face CD, that is on the opposite face. Shear force tau delta X into 1 on the force BC, the face BC, here at the bottom side, and tau plus d tau by dy into delta Y into dx into 1 on the face AD. Now equating all the forces with a proper component in a proper direction. So when we equate them horizontally, considering the horizontal direction, then this is the equation we will get. So after simplification, finally we will get to dou P by dou X is equal to dou tau by dou Y. So this is pressure distribution. So this is the equation of pressure distribution. Likewise, from this pressure distribution, dou P by dou X, we can find out velocity distribution, where dou P by dou X is equal to dou by dou Y of tau. Tau is nothing but mu into du by dy as per the Newton's law of viscosity. Now, using this one, we'll derive, that is mu into dou square by dou Y square into u, integrating du by dy is equal to 1 by mu dp by dx y plus c1. Integrating again, you will get the value of u. U is 1 by mu dou p by dou x y square by 2 c1y plus c2, where constants of integration c1 and c2 are obtained from boundary conditions that at y is equal to 0, u is equal to 0, and at y is equal to t, u is equal to 0. Substituting y is equal to 0, u is equal to 0 in the equation above, that is 3.15, we will get constant c2 is equal to 0. And substituting another boundary condition at y is equal to t, u is equal to again 0, because it is two stationary plates. At y is equal to 0 means at this point, you can see this is the y is equal to 0 point at the bottom surface. Y is equal to t means at the top surface. Now, as you can see, substituting both, you will get the values of c1 and c2. So c1 will be 1 minus 1 by 2 mu dp by dx into t. Again, substituting the values of c1 and c2 in the equation 3.15, what we have discussed, that is the velocity equation u. Now we will get to eliminate the values of c1 and c2. Finally, we will get the equation u is equal to minus 1 by 2 mu dp by dx ty minus y square. So this is the equation where mu, you can see here, dp by dx pressure distribution, and T are constants. So in this way, U only depends upon the Y. So that is nothing but the velocity varies with respect to Y. So here the velocity varies with a square of Y, because here there is a square, and the above equation is known as equation of parabola, because as per the following figure, the velocity distribution across the section of parallel plates is parabolic. So this is the velocity distribution figure. As you can see, the velocity at the walls is almost zero. The velocity at the axis or at the center of the two parallel plates is maximum. Likewise, the shear stress at the wall is maximum because here there is no velocity, and shear stress at the center of two parallel plates is zero because it is having the highest velocity at the center. So this figure fortifies the velocity distribution and shear stress distribution across the section of parallel plates. Now in continuation of the same derivation, we will have the equation for maximum velocity. So we know that maximum velocity occurs at the center. Okay, therefore at the center, what is the value of y? Y will be, so this is the direction of y. Y will be half of the gap. So that is nothing but half of the gap is nothing but t by 2. Substituting this equation in the above equation of u, that is y is equal to t by 2, then you will get this equation 1 by 8 mu dp by dx into t square, where this is equal to maximum velocity applicable only at the center of the two parallel plates, gap between two parallel plates, that is t by 2. Here the average velocity u bar is obtained by dividing the discharge q across the section by the area of the section. Now, so discharge q, when it is divided by u, then we will get the average velocity. The discharge q is obtained by considering the rate of flow of fluid through the strip of thickness dy and integrating it. Now you can see that dq is velocity at a section at a distance y and area of the strip. We know that q is equal to area into velocity. That is what the equation, the continuity equation, has been used. Now velocity at a distance y can be written by minus 1 by 2 mu dp by dx ty minus y square equation. This is the velocity distribution equation, and area of the strip will be dy into 1. So unit thickness is considered. Now q will be 0 to t dq. Okay, so integrating the dq from 0 to t, we will get the value of q. So this is the equation for the q, that is minus 1 by 12 mu dp by dx into t cube, where we have to determine the average velocity. That is nothing but, we know the q is equal to area into velocity. Okay, a into u. So here average velocity is nothing but q by a. So since it is average velocity, instead of u, I will write u bar. So substitute again the same expression of q what I have got here, that expression here, and area is t into 1, substitute thickness into 1. Now u bar is this equation, average velocity also we will get. So we got u bar, u maximum, that is maximum velocity at the center. The ratio of u maximum by u bar you will get by substituting these two equation, corresponding equation. Dp by dx into t square will get cancels, only mu also get cancels, only 1 by 8 divided by minus 1 by 8 divided by minus 1 by 12 will remain. So the final equation will be 3 by 2. So this is what the lengthier derivation. There are 4 to 5 subsections in this derivations. You have to by heart the properly the entire derivation and practice it so many times, so that it is very important from the exam point of view. You should be able to derive every point, so every expression of this derivation. So next one is drop of pressure head for a given length. Now u bar, we know that I have written the equation, dp by dx is nothing but drop of pressure head, or P1 minus P2 is the difference in the pressure, drop of the pressure. We know that dp by dx is equal to minus 12 mu u bar by t square. So dp is what we are having the interest, that is p1 minus p2 after integrating from 2 to 1. So on the RHS also we integrate from 2 to 1 the x, the distance from x1 minus x2 we will substitute here. After simplification, finally we will get p1 minus p2 is equal to 12 mu u bar L by t square, where L is the two sections, two positions, x1 and x2 are some arbitrary positions, and the difference of x1 minus x2 will be the length of the direction in which the fluid is flowing, where hf so is one more derivation we have to derive, that is a drop of pressure head. Hf is equal to P1 minus P2 by rho g, that is P is equal to rho g H, hydrostatic law. So using that one, we have to derive this one. Hf is equal to P1 minus P2 by rho g, where Hf is equal to 12 mu u bar L by rho gt square. So how you got this one? By substituting this P1 minus P2 value as 12 mu ut ul by t square. Here I have substituted, and rho g as it is I have kept. Now this is the figure which represents the drop of pressure head for a given length. So this is section 1, section 2. X1 is a position from the origin at section 1, x2 is the position of the section 2 from the origin. X1 minus x2 will be the length. Now shear stress distribution also we have to derive. We know that from Newton's law of equation, this one, shear stress, Newton's law of shear stress. Now tau is equal to mu into du by dy, where mu is equal to du by dy into u. U expression is nothing but velocity distribution we have derived in the earlier section. Substitute that as minus 1 by 2 mu dp by dx into ty minus y square, and after the differentiation and final equation, we will get tau is equal to minus 1 by 2 dp by dx into t minus 2y. Again in this equation, dp by dx is constant, t is constant, and the tau depends upon the y. Okay, so here tau varies linearly with the y, with a maximum when it is y is equal to 0 or y is equal to t. That is, shear stress is maximum when y is equal to 0 or y is equal to t. This is what I have shown in this figure. When y is equal to 0, this is the position when y is equal to 0, and this is the position when y is equal to t. The shear stress you can see at the wall is maximum, and when y is equal to t by 2, the shear stress is minimum, whereas the velocity is at the center is maximum. So that is what they have discussed. Finally, maximum shear stress, that is at walls, can be obtained by this equation. Tau naught is equal to minus 1 by 2 dp by dx into t. So this is the various expressions of the two stationary plates of fluid flow between two stationary plates we have derived. So let us solve one problem on this one. There are two parallel plates kept 100 millimeter apart, having laminar flow of oil between them with a maximum velocity of 1.5 meter per second. If velocity of the oil is 24.5 poise, calculate the following. What are they? They are discharge per meter width, shear stress at the plates, difference in pressure between 2 points 20 meter apart, velocity gradients at the plates, the velocity of oil at 20 millimeter from the plates. So these things we have to calculate. Write down the data. T is equal to 100 millimeter, that is 100 into 10 to the power of minus 3. This is nothing but, if you are having two plates, this is the gap between the two plates, T. Okay, u maximum, that is mu maximum will happens at the center, that is maximum velocity at a t by 2. Mu viscosity 24.5 poise, that is 24.5 divided by 10, which is equal to 2.45 Newton second per meter square. Next, y is equal to 20 millimeter, that is 20 into 10 to the power of minus 3 meter distance from the plate we have to consider. Find out what? Q discharge, shear stress at the wall, it is at here, P1 minus P2, pressure difference between the 20 meter apart, du by dy velocity gradient. Now we know that u maximum is equal to 2 by, sorry, u average velocity u bar is equal to 2 by 3 times of u maximum. So substituting 2 by 3, u maximum we know that is 1.5 meter per second. Substitute, you will get the answer, average velocity u bar is equal to 1 meter per second. Now discharge is equal to what? Q into A. So Q is equal to area into velocity. So this is representing the area, cross sectional area. This is average velocity, that is average velocity 1 into 100 into 10 to the power of minus 3 is t into 1 meter, that is width I have considered. Therefore Q is equal to 0.1 meter cube per second. Now difference in pressure between 2 points 20 meter apart, then u bar is equal to minus 1 by 12 mu dp by dx into t square. So u bar is nothing but 1. Substitute 1 by 12 minus 1 by 12 into mu 2.45 given in the problem. dp by dx as it is, you keep it as it is because it is unknown. T is 100 into 10 to the power of minus 3 whole square. Solving, you will get minus dp by dx is equal to 29440 Newton per meter square per meter. Rearranging, we will get minus dp as 2940 dx. Integrate between the limits p1 to p2. Then finally you will get the pressure difference p1 minus p2 as 58.8 kilonewton per meter square. So it is still not yet complete. We have to determine shear stress at the wall. Shear stress at the wall is nothing but tau naught. First we put the equation of tau, write down the equation of tau we know. Next, at y is equal to 0, tau is equal to tau naught, means at the wall when y is equal to 0, tau is equal to tau naught. Substitute, you will get minus 1 by 2 dp by dx into t into 2 into 0 to y. At y I will put 0. So the equation reduces to this. Okay, and substitute 1 by 2 dp by dx minus dp by dx value, it is in minus only. Minus dp by dx is plus 2940, substitute into t 100 into 10 to the power of minus 3. Therefore tau naught is equal to 147 Newton per meter square. Now velocity gradient at wall we have to determine what is the velocity gradient. For that we can use the equation tau is equal to mu into du by dy, where tau naught is equal to mu into du by dy at y is equal to 0. Substitute to tau naught as 147 is equal to 2.45 into du by dy at y is equal to 0. Substituting and solving, du by dy at y is equal to 0 is equal to 60 1 over second, or second to the power of minus 1. This is what the velocity gradient at the wall. Now finally velocity of the oil can be found out by the velocity distribution equation u is equal to 1 by 2 mu minus dp by dx t into y minus y square. You know the value of mu minus dp by dx as 2940, mu as 2.45, t as 100 into 10 to the power of minus 3, and y as 20 into 10 to the power of minus 3. Substitute all, you will get finally the velocity of the oil as 0.96 meter per second. So in this way we have done today the viscosity of the fluid between two parallel plates derivation. And then the next, there are several problems based on these equations. In the next class we will study this expression, that is viscous flow of viscous fluid between two parallel plates. So here it is also similar to that earlier one, but here one plate is moving and another plate is at rest. You can see that the top plate is moving plate and the bottom plate is at rest. So this type of flow is also very popularly known as covet flow. We are going to study the same type of derivation once again in the next class with the same expressions, but here there is a one plate, bottom plate is fixed and another top plate is moving plate. That is the only difference. So we will do one problem and a derivation in the will be continued in the next class. You please go through this video several times until you get familiar with the above derivation, because from the exam point of view this is the very important derivation. So with the intention that you can view it many times, whenever you are having a doubt, and write down entire derivation. I am doing this video and uploading to the YouTube. Kindly go through it, and we'll meet you in the next class. Thank you.